Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about LiDAR, a technology that's revolutionizing many industries, including self-driving cars, farming, and the GPS industry. Specifically, we're going to talk about optical phased arrays, a new technology that makes LiDAR sensing much more effective. What LiDAR is that it's a light beam that moves across space, scanning, and when it hits something, that light reflects back, and a sensor measures what the light is when it comes back, how long it took, and therefore it can tell what's around it. LiDAR needs to scan space, not just measure straight ahead. So there has to be some way to move a light beam across a field of view. This requires steering a beam of light. And the early solutions to this were mechanical. They had mirrors that turned on swivels, and then that light reflected off the mirror and came back from an array of angles. The challenge with this is that there were size issues, cost issues, and it was oftentimes unreliable. Mechanical gears and pulleys and things wear down. They're more likely to fail than pure electronic components. The reason it's a bottleneck is because these rotating assemblies wear, vibrate, and fail eventually. They're also very large. Having these mechanical components take up a lot of space compared to electronic chips. They're hard to mass produce, they're hard to shrink, and cars, drones, and all sorts of infrastructure suffer when they need more space for these things. The revolution is optical phased arrays, and they take advantage of the fact that light behaves as a wave, not just a line that shoots outward. These waves can interfere with each other, constructively and destructively. And essentially, what optical phased arrays do is they use these interferences to make a beam that essentially travels in one direction. The steering doesn't require physical control, only the precise tuning of these waves to have very specific properties that allow it essentially to just point in one direction. An optical phased array is many emitters instead of just one for mechanical techniques. They all produce light waves simultaneously, with small timing differences, amplitude shifts, phase shifts, and when they all combine together, it points in one direction. And as they shift that phase and the amplitude slightly through time, that direction changes by a little bit. And ultimately, it sweeps across a field of view so that a computer can get an understanding of what it's seeing in front of it. Eventually, this allows GPS systems to map out the bottom of our ocean. It allows self-driving cars to detect what's in front of them. It allows LiDAR to become much more efficient and effective. The phase is the most important of these things, and it's used as a control knob to control where our light beam is generally pointing. It's a relative timing between all of the emitters, and how they work relatively controls where it points. Small delays between each of these emitters are very, very important and precise in generating the result that we want. This nanometer-scale precision, even just a few billionths of an inch, maybe not billions, maybe millions, can contribute massively to where the thing is pointing and where the sensor can detect information. So what is an OPA, an optical phased array? What is this physical structure? So it's a chip-based system. It's an electric chip that you can put in something, and it shoots out little waves. Inside the chip, there are thousands of waveguides. These are little tunnels for light to travel through. It bounces off the sides, and it carries light to where it needs to be released. Inside these waveguides are wave-shifting regions, or little stations, where it can shape the phase, the amplitude, whatever it needs to change in the light, so that it's very precisely tuned to create the result it wants. Eventually, the waveguides end up at a series of microscopic emitters. These are what actually do the emitting, and are the final step in the light release process. The big important thing is that here there is no macroscopic motion. There's no big change. There's no gear that's turning that can wear down over time. It's small, precise, and ultimately the superior type of LiDAR sensor. So how does this beam steering work in practice? What happens is that light enters the chip. And then when it enters the chip, it's split into multiple paths, into these many waveguides. These phase adjustments are applied, and once it exits, it achieves the phase pattern that's needed to interfere and point in the direction that we're looking. This allows LiDAR to become faster at scanning, more reliable eventually, and it has much smaller footprint, meaning that it's much easier to integrate into something like a car or a drone. Additionally, it could have potential cost reductions once many of these are made, and the infrastructure for making these is much stronger. Additionally, it is more compatible with other types of manufacturing, meaning that some of the infrastructure in the production process has already been built, and therefore it might require less work than, say, a giant gear system would. Unfortunately, these systems come with trade-offs. Firstly, the beam width can be an issue. Since these OPAs are much smaller than traditional systems, the beam width, the final light beam that they're sending out, is much smaller. This means that it's harder to capture a large field of view in a small amount of time. This could mean that we need to add more and more of these arrays, these chips. But that takes up more space and creates the problem we were solving in the first place. Fortunately, though, with these smaller beam widths, we have higher resolution. We're more able to photograph smaller places. This is another huge advantage. But again, it's more important for a self-driving car to be able to see everything around it rather than to be able to tell the height of a sidewalk or exactly how tall a person in the road is. Another challenge is what we call side lobes. When these light beams are passing through waveguides, if they hit a little tiny bump in the structure, they could reflect off completely differently. These reflections are what the side lobes are, and they can be big problems. If a light goes in some unknown direction, then the beam that we were trying to create is now smaller. This smaller beam is labeled to take less information back, and it's able to give less information to the computer. It also could get information that's entirely wrong because there's something missing. Maybe they won't be able to see a specific section because there is no light coming back from there. These massively affect LiDAR accuracy, and it's not just a software problem because the very chip itself is the issue. The chip needs to be manufactured super precisely so that we can avoid these issues. Biggest strategies is to make our emitters better distributed. With more properly larger gaps between the emitters, we're able to reduce manufacturing issues. Additionally, we can specifically make our phase pattern or our light waves in a specific way that, while keeping our same light direction, we are able to modify how they bounce through the tubes, and therefore we are able to reduce the impact that a side lobe would have. Finally, there could be some software, maybe using artificial intelligence, that can recognize when there is a side lobe and when there is an error in the image that we're getting back. That would help mitigate the errors and potentially be able to fill in what information we might be missing or the information that might be clouded or ruined. So the most important part of this system are the phase-changing regions, the regions inside our waveguides where we're able to tune the light to be in the exact wave pattern that we want. How does this work? Right now we use thermal phase shifting, or we just heat up the waveguides. And what that does is it changes the refractive index of the situation. That means that the light is going to bounce differently through the waveguide, and eventually it will have a slightly different trajectory and phase pattern when it leaves. Unfortunately, we have to heat up this tube, which requires time, as it takes a long time to heat up something that might be made of silicon or another material, and it takes a lot of power. The biggest issue, though, is that the waveguides are incredibly small, and heating up such a small thing isn't very possible. The heat can spread outward, warming up something else, leading to imprecision. These thermal warmings in one place spread to another, causing changes in other waveguides and other light beams. This is called thermal crosstalk, and it can ruin the whole thing. To solve this problem, we're taking completely new phase control approaches. The primary that is being developed right now is electric field-based phase shifting, meaning that we scrap the whole heating idea and we create electricity pretty much throughout the chip. Similarly, it changes the refractive index, creating different bounces, but it's much easier to tune precisely. Additionally, you can turn it on and off quickly, meaning that it doesn't take a long time to get the chip ready to work. And it can require less power, partially because it's much more precise and easy to do. But again, with both of these, both the thermal and the electric field-based phase shifting, materials are very important. For thermal especially, you have to have something that conducts heat in just the right way, and it can be very hard to fabricate something. Oftentimes, these materials need to be made specifically for the purpose, and materials scientists are working on that. These materials can help control the refractive index, meaning that it will bounce differently off of different materials. In different waveguides, we might need different materials. Silicon will have something have a larger amplitude, and therefore it reacts differently and moves differently. Additionally, some materials can have optical loss, meaning that the light is absorbed by the material as it bounces around in the waveguide, meaning that it's not as strong when it exits and therefore can't convey as much information. Silicon is the easiest material, but it suffers from limitations. And while it has worked for many computer chips in the past, we're going to have to come up with something new to be particularly effective in this industry. Right now, scientists are working on creating their own material specifically for this, something that's never been made before, to allow precise refractive index, minimize the optical loss, and overall create precise light waves to achieve our purposes. Again, the biggest problem here is making incredibly precise waveguides. This will allow us to succeed and create accurate images for our computers. So, how are these OPAs used today? These optical phased arrays are primarily in LiDAR. That is used in short-range sensing in things like cars, can be used in drones or other types of robotics, and optical communications across super long distances where it can launch light beams into space to communicate with orbiting objects, and all sorts of other applications. Not everywhere yet because of very specific limitations where the manufacturing is the biggest one, but also, materials that we're developing, cost, lack of infrastructure, lack of understanding. Additionally, it's not very mature yet. It requires much proof before it's used in these important industries like medicine or space travel. Being able to create larger, effective arrays that actually are precise, having materials that have less optical loss and less flaws in them, having better light sources that we shoot into our waveguides and shoot into our chips, and having better calibration will all make them much easier to adopt on a wide scale. This helps all sorts of things: optical communication, steering beams in space, creating holograms even, and maybe even in the future work on quantum computers. All of this could be created with optical phased arrays. So the big picture is that optical phased arrays can help LiDAR by shifting away from this mechanical motion, these gears and mirrors, to very precise control. This is similar to early transitions in electronics. These concepts start out very physical, and then they move toward these more abstract, smaller, more efficient solutions. This precision replaces big movement. It'll allow us to have things in cars where you can zoom in on a person in a sidewalk so that you can have more information and learn faster. It can be super highly reliable if these manufacturing errors are fixed and we can have more consistent materials. And it will be more seamlessly integrated than our current LiDAR solutions. OPAs can allow us to intentionally shape wave behavior, intentionally shape light. They can allow us to see the world in a whole new way.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.